Hey everyone. So today we worked on equivalence relations, and I know a lot of you weren't able to make it to class this morning, which is fine. But I would strongly recommend that you look through the lecture notes and also try to work through this worksheet on your own before proceeding with this video. So number 1 says, let X denote the set of all finite subsets of N. So basically we have the natural numbers, and that includes 0, 1, 2 to infinity. And then we have X, which is the set of all the finite subsets. So it's going to be a set of sets. You don't have to fully understand this in order to do this problem, but I just feel like showing it to you anyway. So it'll be like this set of 0, 1 to the set of infinity, and then it'll start being the set of two numbers, 0, 1, 0, 2, and it's a really big set. Let's just say that. It's a lot bigger than the set of natural numbers because it includes all the natural numbers, but then it includes every subset of the natural numbers as well. So that is the set that we're working with. And we wanted to find a relation on elements of X. So we're going to take a couple elements of X. Let's say this is one of the elements and that's one of the elements. And S1 tilde S2 means that the cardinality is the same, that S1 equals the cardinality of S2. So that's what this tilde is, basically shorthand for cardinality equality. And when you think about all these equivalence relations that we're going to be working with, or even if they're not equivalent, tilde is like a stand-in for some longer phrase. So tilde here means the cardinalities are equal. So if you see S1 tilde S2, that means that S1 and S2 have the same cardinality. So for number 1, we want to show that this is an equivalence relation, and there's three steps of equivalence. I'm not sure if I spelled that correctly. Yeah, I think it's good. Okay, so 3 steps of equivalence. The first one is called the reflexive property, number 1, and kind of like with induction, these equivalence problems follow kind of a step-by-step sort of guideline where you have to show that these 3 properties are all satisfied. The reflexive property is for every S1 in X. Remember, these S1 and X2 come from X over here. That's where they're coming from. So they're subsets of the natural numbers. That's what S1 and S2 are, and they could be of any length. It could be of cardinality 1, like these sets 0 and the set of 1, or it could be cardinality 2, like 0, 1, and 0, 2, or it could be infinite cardinality. It could be the entire set of N, because the entire set of N is in X. Hopefully that's clear. X contains all the subsets of N, including the entire set of N. So for every S1 in X, S1 tilde S1. That's what reflexive means. Now we have to see if it's true in this case. And here, tilde means that the cardinalities are equal. So S1, the cardinality of S1 is equal to the cardinality of S1. That's a trivial statement, but we have to show it. We have to say that it's true. So is true. So tilde is reflexive. Step 2. That was pretty easy. Now we want to show this thing called symmetry. Symmetry says that this is, so reflexive is just X tilde X, or S1 tilde X S1. And we have to show that equivalence relation works kind of reflexively onto itself. Now, for symmetry, we want to show that if S1 tilde S2 is true, then S2 tilde s1 is true. Another way of saying that is s1 tilde s2 implies s2 tilde s1. So that's what we have to show for symmetry. And here we say, well, s1 tilde s2 means that the cardinality of s1 equals the cardinality of s2, which is equivalent, or it implies that the cardinality of s2 equals the cardinality of s1. And that's exactly what this is saying. So that's clearly true. It's true. Okay, so we have symmetry. We've shown that this equivalence, that this tilde, meaning that the cardinalities are equal, is reflexive and it's symmetrical. Now the third property that we need to show is that it is transitive. Transitive property. And you guys know the transitive property. It's like A is greater than B and B is greater than C, then A is greater than C. That's like an example of the transitive property. So you could probably guess, even if you didn't look at the lecture yet, that, which you should, then basically what we're saying here is A tilde B and B tilde C imply A tilde C. That's what we have to show here. And here I'm using A, B, and C instead of S1 and S2 and S3 just to show that you can. You can use any variables you want, except I wouldn't use X because that's like A, B, and C here are all subsets of X. They all are subsets of X, and X comes from the natural numbers. So these are, you could think of A, B, and C as sets that contain natural numbers. And we are concerned with their cardinality. How big are those sets? What's the size? So here we would say that if we are assuming these first two properties to be true, we are assuming A tilde B and B tilde C, and we are wondering, does that imply that A tilde C or not? And if it does, then we have an equivalence relationship. Then we could say that tilde is an equivalence relation. So we have the cardinality of A is equal to the cardinality of B, and the cardinality of B is equal, yeah, okay, that works, equals the cardinality of C, and that implies, put all that in parentheses, so we're using both things, and that implies that the cardinality of A is equal to the cardinality of C, and true, therefore tilde is an equivalence relation on X. And that's the set that we're working with. We're taking subsets of X. Okay, so that's number one. It's pretty trivial, and you'll see number two is also kind of easy, I think. Although the way the problem's posed, it's a little bit harder to think about maybe. So we'll work on number two now. So number two says, let S be the set of all quadratic polynomials. So S is a set. So that's our set notation. It's a set of all quadratic polynomials with real roots. And we're actually given what this looks like. So it's f of x. So it's a set of functions, quadratic functions, ax squared plus bx plus c, given or such that a, b, and c are all real, and b squared minus 4ac is greater than or equal to 0. Many of you know from other classes you've taken probably that b squared minus 4ac is called the discriminant. And if it's greater than or equal to 0, that means that we're going to have real roots. So if we set ax squared plus bx plus c equal to 0, we'll get like x plus something times x plus another thing. And we could find these real roots where x equals like this or that. And we've all done algebra problems like this. So what this problem is saying is, okay, and then we have relation tilde, relation tilde on S defined by f tilde g if and only if f and g have the same zeros. So let's understand what this means in English. We have this function f of x and it equals something, and we could set it equal to 0 and find the two zeros of it. And then we have another function g that equals something, and we could take the zeros of that function, and what we're saying is if f tilde g, that means that they have the same zeros. That means that you could set the functions equal to 0 and get like x equals 3 and 5, and for g you'll also get x equals 3 and 5. And so that's our equivalence relation. That's what, when we say f tilde g, that's what we mean. So in the previous example we said f tilde g would mean, or s1 tilde s2 would mean that the cardinalities are the same. But here we're working with a totally different set, and we're redefining this tilde, we're redefining it, and we're saying f tilde g means that they have the same zeros, their functions have the same zeros. So now we have to ask those same three questions that we asked before. The questions of reflexive, symmetry, and transitive. Do they satisfy all those properties? So 1, reflexive. And hopefully you could already start thinking ahead and understand that f tilde f means, I think it's helpful to define these things, that you don't always have to, it means that f and f have the same zeros, which is true. Oftentimes, the reflexive property is trivial. It's not always the case, but here it is. So 2, we have symmetry. Yeah, okay, so symmetry would mean that f tilde g implies g tilde f, and that first statement means f and g have the same zeros, implies that g and f have the same zeros, and that's also obviously true. True. When it's really trivial like that, you don't have to demonstrate it. This is like how you demonstrate it. You just write it like this. This is all you need to do to complete a problem like this. Okay, number 3, transitive. And I'm running through this because I think it's really easy, and I want to get to the harder one, which is number 3. And yeah, okay, so transitive. This one says, here with the transitive, we have to introduce a third variable. So transitive again means f tilde g and g tilde, let's say h, because that's the next letter, implies f tilde h. That's what the transitive property says, and we have to show that that's true. So f tilde g means f and g have the same zeros, and g and h have same zeros means f and h have the same zeros. Okay, so that works. So we're good. So at the end of the proof, you could just say that tilde is an equivalence relation on S. That's kind of how you would, that's sort of like the conclusion. All right, let's jump into numero trace. Okay, here we're going to define a relation tilde on z by x tilde y if and only if x minus y is even. So now x tilde y is true if their difference is even. That's interesting. That's a little different than the other stuff we've been doing. It's not exactly an equality. Like in the first one, I'm scrolling back to number 1. I'm hoping that all my scrolling isn't disorienting, because I realize that I know exactly when I'm going to scroll, but you don't, so it might surprise you. Anyway, the first one said that tilde meant that the cardinalities are equal, and the second one said that tilde meant that the zeros are equal. Here we're not saying anything is equal. Here we're saying that their difference is even. It's a very different way of thinking about this problem. Because you can imagine if x is like 6, for example, x equals 6, then y, for this to be true, for their difference to be even, y could be any even number. Y could equal 4, and their difference is 2. Y equals 18, and their difference is negative 12. All those are even numbers. So here it's not, telling you what x is does not actually tell you a whole lot about y, except that it's even, and that's going to get us to the last part of the proof, or the last question, which I'm going to talk about even though we didn't do it in class today. So x tilde y means that the difference between x and y is even. So to show that it's an equivalence relation, what is the first step? We have to say that it's reflexive. One is reflexive, which is x tilde x, means that x minus x is even, right? I'm just substituting. Here, let's do it like this. This x and this x for that y, so the x's go here. Or rather, this x goes here, that x goes there, and I have x minus x is even. And x minus x equals 0, which is always even, is true. Great. So x minus x is 0, 0 is even, therefore this is true. You could already see that we're doing a little bit more actual math in this problem. We're not just saying that they're equal. We actually are subtracting x from x and getting a number. So part 2, symmetry. Hopefully this is getting like easy to the point of boring for you. Okay, x minus y, or let's use the proper notation here. X tilde y implies y tilde x. That's what we need to show. So x tilde y is the statement that x minus y is even, and that should imply that y minus x is even. So let's actually introduce some variables. You don't have to do it this way. I just think it's the easiest way to do it, and it's Arya likes to recommend this a lot, and I think he's right. I think that this is the best way to visualize these type of problems, is to substitute is even for some actual variable. So let's say x minus y equals 2k for some k in z. Right, we're familiar with this kind of notation. So x minus y is even. That's what this means. And y minus x, there's two ways of going about this. We could say, well, now we know that x is equal to 2k plus y, and y is equal to, what is it, x minus 2k. So y minus x equals x minus 2k minus 2k plus y, which is equal to x minus 2k. So it's equal to x minus y. What did I just do? X minus y, y minus x. I did something wrong here. X minus y equals 2k. So x equals 2k plus y. That's right. I added the yk. I said y equals x minus 2k. That looks right. Whew. So then I said y minus x, which is over here. Y minus x equals x minus 2k minus 2k plus y. Oh, I see where I went wrong. So I actually want hopefully some of you guys caught my mistake. So it's actually x minus 4k minus y. And we already know that x minus y, we could also write this as x minus y minus 4k. And we know that this is equal to 2k. So this equals negative 2k, which is even. So it's true. a much simpler way of doing this, if you're able to recognize this, is that x minus y equals negative y minus x. So if this is equal to 2k, then that is equal to negative 2k. That's like the quick and dirty way of doing it. But this way, the way that I just showed you, where I did all the algebra, totally works and is like more generalizable. It's more general because that way will always work. And this was just a cheap trick. So now, for number 3, we want to show that x tilde y and y tilde z imply x tilde z. What does that mean? It means that if x minus y is even, now I'm going to already start doing it like this, and y minus z equals, let's say, 2l, they're both even, that implies that x minus z is even. And I'm not going to give the variable yet because I'm going to do algebra to try to figure out exactly what x minus z is equal to. So now I'm going to do the algebra. So I know that x is equal to 2k plus y, right? Just doing algebra on this. And I know that z is equal to y minus 2l. So x minus z, hopefully I won't mess this one up, is 2k plus y minus y minus 2l, whoopsies, which is equal to 2k plus y minus y, the y's cancel out, and minus a negative 2l is plus 2l, which is equal to 2 times k plus l, and I forgot to define k and l as integers, but k comma l in z, I know I'm a mess, but you hopefully know what I mean, which is even, so it's true. We just showed that x tilde y and y tilde z, if both of those are true, that proves, that implies that x tilde z is true. And x tilde z is the statement that x minus z is even. And so we just showed that x minus z equals this, which equals this, which equals this, which is even. Yay! Okay, now for part B, we didn't do this in class, and Professor Carbone did not do this in class today. She didn't teach this material about equivalence classes, which is what part B is asking you about. So you don't need to do this yet. You should probably watch the lectures before doing these problems. I just want to give you an intuition for what it means. Remember earlier how I was talking about if x is 8, for example, if x equals 8, for this statement to be true, for x minus y to be even, we just need 8 minus y to be even, which means we have like 8 minus y equals 2k for some k in z, and 8 minus 2k equals y. And since k could be any integer, the difference 8 minus 2k is just any even integer. You could make 8 minus 2k equals 0, you can make it equal negative 2, you can make it equal negative 108, you can make it equal 300, depending on what you sub in k for. So saying, so in this case, y could be any even number. And similarly, if x is an odd number, let's say x equals 7, y can be any odd number, any little o and big O. It could be any odd number. So what these equivalence relations are is basically saying, let's say instead of subbing in a number for x, we sub in a number for y. Let's say y equals 0. So now we have this x minus 0 is even. So that's true if x is even. So basically all we're saying is that x has to be even. X could be any even number. This is true whenever x is even. This is true. So the equivalence class of 0 in this case is any even number, any even x. And the equivalence class for 1, if you're going to take away 1 from x, so we have now x minus 1 is even. So this is true whenever x is odd, any odd x. So it's okay if you don't fully understand this yet. We haven't covered it. And there's just one last little thing that I wanted to show you guys that we mentioned briefly in class today, but it's not on the worksheet. Not every tilde, not every relationship is an equivalence relationship. For example, let's say we have tilde, let's say x tilde y if and only if x is less than y. Let's say that's what the tilde means here. That's what our relationship is. Is that this x tilde y is true as long as x is less than y. Then if we try to show that it's reflexive, x tilde x means x is less than x, which is not true. Not true. So tilde is not reflexive. That's just an example of where things could go wrong and where you might see that something is not an equivalence relation. So I just wanted to show you that so you don't fall into the trap of thinking everything is an equivalence relation, because certainly not everything is. And you do have to demonstrate and be convincing about it that something is actually an equivalence relation. Anyway, I won't be seeing you guys tomorrow. We don't have class. So happy holidays, happy Thanksgiving, and enjoy.